So, uncertainsystems.com. Good. So this is going to be a short one, actually. I basically want to show you guys and walk you guys through a small modification that I did to Quirk and I'm testing right now. I haven't really had time this week to work on this more. It was more sort of something that I worked on last 2 weeks ago or something like that. But I just wanted to go through these and explain a little bit more what do I have in mind. And hopefully we're going to see some code as well. Although you might probably, just be horrified of how I did this. The current thing is just a copy paste Frankenstein of Craig's existing and really well written code for the rest of Quirk, right? But basically, so let me just give you a quick introduction to what I kind of had in my mind and what I wanted to do, right? And it all goes back to the notion of kind of some of the problems that you have when you use the mathematical model that's used for quantum computing to reason about algorithms. And I always kind of had that feeling that you're missing some stuff, right? For example, when you do a Hadamard gate, right, and then you do another Hadamard gate, you kind of go back to zero, right? Now, if you basically go and apply the matrix operations for the Hadamard gate to that initial state, that just kind of gives you that same outcome, and that makes sense. But I kind of realized that this is where interference is really happening, right? Because you don't I have my drawing tools in here? I sadly don't have my drawing tools here. But you turn that 0 into a 0 plus 1, right? Maybe, can I just use itty-bitty? I think this is something called itty-bitty site. We can just like randomly type in stuff, right? So let me see if I can zoom in a little bit. If you have the 0 state as your initial state, right, and then you apply a Hadamard gate to it, then you're going to get into the 0 plus 1 state. And I'm kind of omitting here on purpose the normalization stuff, and just for the sake of simplicity. And so when you apply a Hadamard gate again, you can also think of this operation as you're applying it to each of those components of your superposition. And so if you've got a 1 and you're applying a Hadamard gate, what you kind of get, let's use actual notation for this. So I'm going to use Hadamard times h, right? Hadamard times 0, as in like the Hadamard gate being applied to that state. I think that's the proper way of doing that. So what you have is these, right? So now if you are at the state, if you apply a Hadamard at the state 0 plus 1, it's the same as applying Hadamard to the state 0 plus applying Hadamard to the state 1. And so, and if we basically put all that together in here, then you basically get to that to this expression where you kind of see there's a plus 1 and a minus 1 that cancel out. And so this is, you could think of, this is being the destructive interference taking place. Now you don't see that when you apply the matrix for the Hadamard for a 2-qubit system, because that part in here is hidden within the matrix multiplication, because you're multiplying the different elements of different rows and columns, and then the thing adds up, and that's it, right? So, and I always wonder that, whether there will be a way to do that so you could see those patterns before they happen, and that would help you understand algorithms like Grover's algorithm a bit better, because at the end of the day, what Grover's algorithm is just a tweak on those phases right before you apply the second Hadamard gate to this state, so that instead of destructive interference, you've got constructive interference, right? So right. So I went ahead and I did that here. So basically, I created this inspect interference button here, where just to give you an example, we'll work on a 2-qubit system, and then you kind of see here that if you would apply two Hadamard gates again, then we're back at 0, 0, right? But if you add a sort of a control Z in here, now you're not going back to that state anymore, right? But you're going back to that state in here. So if I would like to take a look and kind of have a tool that allows me to see what is the interference pattern that's happening here, because maybe I can tweak that to then, kind of create a certain effect without having to go kind of back to the math and trying to figure out in a more abstract level what I should do. So what this is doing is this is kind of copying the same interface that you have when you click on make gate. So that part here, just because I'm lazy, and so you can basically tell this guy, show me what's going on between like right before this operation and right after this operation, right? So if you do these, you get that kind of table here where you've got the initial states, possible states of what your superposition would be of all the possible states of the system, of a 2-qubit system. And then you kind of see grayed out all the states where it's, the coefficient is 0. And it's just, you're right before this gate, it's everything, it's all your probabilities, all your amplitude is here in the 0, 0 state. So after you apply the two Hadamard gates, basically that gets transformed into an equal superposition. Which kind of, this is a new way to represent that it stems from that state, right? Not from any other state. Now, if I move to the next, right, the Control Z, and I click on these, then you see that, what we had in this column is now moved to this column. But now it's really interesting. You see that the Control Z has basically spread out the. It hasn't only. That's what fascinates me. It hasn't only changed the phase of the 1-1 element, which is what you would expect mathematically, but it's also shifted things around. Like it's also spread things around these other boxes in here instead of keeping them here. Right? It hasn't changed the value, but they're kind of spread in here, and this is because. It's kind of coming from this element, so it how would you reason about this? But let's go ahead. So what happens now, right, is that if you take a look at the third operation, which is another Hadamard layer, so you can see that if this is your starting point. The first column is the starting point. And now you're applying a Hadamard gate to each of those boxes. And so they each get field tap. And so this is what's I still have to do some work here because I'd like to color code this somehow so that you basically can see the interference effect better, because it's all white now, so you can't see this. But pay attention that it kind of so nothing is really canceling out, right? Because you have like a plus minus. So there's a bit of canceling in here, right? And so you kind of see what else do you see here? The 0-1 case is plus minus plus plus, right? You can see in the 1-1 case that it's kind of it has a negative advantage. It's minus 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 plus, and so the overall outcome is going to have a minus, and that's what you see here at the end. You see that the amplitude here is minus, right? Now, the interesting part is that when you apply this to Grover's algorithm, you kind of really see where how can you tweak those different patterns in here. So let me play with something. What if I would now say that I want to, for example, cancel out some stuff? Is there anything I can cancel out? So if I if I'm here, if I minus the 0, 0, that will basically turn that around. So if I apply Grover's algorithm, right? So let's say, for example, well, that's almost it, right? So you're here, and then you have the two Hadamarts, the Hadamard layer in here, and now you basically want to do these, right? So you wanna finish your amplitude amplification, and you end up just with these case. So let's analyze the interference in this circuit, right? So how could we do it? So if I do so if I take a look at these 4, 5, 4, 6, what do I see, right? So I see that part in here. I'm not so sure that's working well though. 4, 5. Yeah. I'm not so sure it's working entirely well. Anyway, but you get the idea, right? So I gotta try to see if I can fix that though. This is basically inspired. Was inspired by one of my Grover videos where I was doing this by hand, and I was kind of like saying, well, if you start here, right, that's what you have. If you go all the way, here, what you end up having is that a superposition with a minus in here, and so when you apply the next Hadamard layer, right, what you have is you have so you have that point in here where basically this is the inverted. It has the sign inverted in all the components because it's the one that you minused. And so if you now manage to basically change the sign of the 0, 0 component, then it's like minus, minus, minus. So wait a second. So what's canceling with what? So this is not canceling at all. Here we've got like plus, minus, plus, and plus. It's not canceling either. Exactly. Now nothing is canceling, but if I minus, if I go all the way, to minusing this stuff. Oh yeah, you've minus the whole 0, 0 exactly. That's what you're minusing. And so now it's when you, that's the whole block that's changing here, right? So that's what so you can kind of see, that actually it is working. So you can kind of see that you can within the range inspect what's going on. So you basically, the whole block has changed to minus, and so now you've got like a minus, plus, plus, and minus, right? And so they are canceling out exactly. So you take a look, they all cancel, minus, minus, plus, plus. They all cancel. Minus, plus, minus, plus, cancel. But the 1, 1 doesn't cancel. And exactly. And so you could have, I wonder whether this is something you could use to, because, yeah, of course, because like you'd wonder, okay, how can I manipulate that state before it interferes, right? So that the things cancel out the way I want. So this is one tool that I'm experimenting with. Maybe, I don't know, maybe this leads into something that's useful for development of algorithms, or for debugging of algorithms, or for better understanding algorithms. That's what's happening. So the whole block between 3 and 7, right? What if I do this? What does this tell me? So I'd have to go 4, 7, I think. Yeah, so if you diff that, if you compare that, that's what the whole block is doing, is it's just minusing that entire thing in here. Maybe there's a way, I don't know, maybe this is somehow useful. Like, how do I get this? So how do I get this? Let's take a look quickly at the code. It's really ugly. So basically I copy pasted stuff around. I'm going to spare you the part of how to get all the windows, all the pops up and all this kind of stuff. It's all really, I'm not ready to share this. I'll open source it, of course, because it's part of, and I'll even submit it as a quick extension, I think, once I'm confident that the code is not shitty. But the only substantial change that I made, aside from copying most of the stuff from other scripts, is that I kind of made up this function called times without interference, right? So in the matrix here, there's this function called times. Basically, it's a function that kind of multiplies the matrices, right? So the only thing that I did is times without is this times without interference. What it does is it does the same. It's a copy of this, but I commented out some of the things, and the only thing that it does is it does not add, like it doesn't add the elements of your multiplication. So when you're, let's see if I can find that. Give me a second. Yeah, here you go. So I was playing with these where I was, kind of getting a state, and this is sort of a matrix that corresponds to a gate matrix. And so what I was doing is what you would do is you'd multiply each element, and then at the end you would add everything up, right? So that's kind of what you would usually see. But what I'm doing with these times without interference is I'm keeping that matrix. So I'm keeping those boxes, and that's what you see in the in those different boxes in here. So it's like if you would add these, and you would add these, and you would add these, and you would add these. This is what you would usually do inherently within the matrix operation, but it's basically what's happening here. So yeah, I think that's, I mean, that's it really. That's all this function is doing, and so I'm using it here to basically get the before interference results and then kind of return them and print them out in the interface. It's really far away from being finished, but I don't know, I'll probably give it another try whenever I have some spare time and see if I can bring it to a state where it's actually helpful. I'm not so sure how this can be helpful, so I'll probably start using it myself in some algorithms and then trying out some algorithms and seeing if that kind of helps me understand a bit more what's going on within a circuit, and how could this be useful to take a look and inspect something before interference actually happens. I don't know. I like it. It seems it's helped me understand Grover's algorithm, because you can take a look at these and you can see, okay, that's the interference. That's where things are being canceled out. Now I understand what that operator is doing, and I don't have to think about rotations in the Hilbert space and whatnot. So that, I don't know, it felt like it was worth sharing. So I hope you guys like it. You can play with it as well. I mean, it's actually, if you go to uncertainsystems.com and then you go to the QuirkMod thing here, so you get that basically a hosted version of this. Again, I don't guarantee the simulator hasn't been spoiled, because I mean, I haven't really played with stuff that might interfere with other parts of the system, but I don't know. I'm not a professional programmer either, so take that with a bit of care, with a bit of with a grain of salt. So don't just expect to be able to use that simulator for for something fancy than just playing around. It's just for testing purposes. You've been warned. Cool. Hope you enjoyed the video. Again, if you like the content, subscribe. That always helps me, and support me as well on Patreon if you want. If you kind of like it, just $1 a month. It always makes me happy and kind of gives me buys me more time to do stuff. And yeah, see you in the next video. See you in the next video.